Hi friends, welcome to the session on physics. This is third session we are going to devote on magnetism. As per SPPU curriculum, these are the three topics we are going to study: origin of magnetism, classification of magnetic materials, and applications of magnetic materials. As you know, the prominent role of magnetic materials is there in the technologies. For example, electroacoustic transducers, speakers, microphones, where we are using combination of aluminum, nickel and cobalt, that is alnico magnet. Similarly, in case of electric motors, meters, magnetic data recording and storage devices, magnetic material is widely used. Basically, magnetic materials can be classified on two different bases. The first one is that whether the magnetic material is retaining the magnetic field permanently or not. According to that, there are two types, hard material and soft material. Depending upon the permeability, there are main three parts of this particular material: ferromagnetic, paramagnetic, diamagnetic. There are two more, ferrimagnetic and antiferromagnetic. Prior to dealing with this magnetic material, we should know the basic terms which are widely used in magnetic materials. The magnet consists of two inseparable poles. These are the North Pole and the South Pole, and this is known as magnetic dipole. As there are two poles, di plus pole is equal to dipole. This is how this particular term is generated. There is force of attraction between two unlike poles, and two like poles will repel each other. This particular magnetic force can be given by F is equal to constant of proportionality into the pole strength divided by square of distance between the poles. This is what I have shown this magnet. Here there are lines, magnetic lines of force, which are starting from the North Pole, going to the South Pole and again coming back to this North Pole. So this is a closed loop where it shows the path of unit North Pole in the magnetic field. Outside the magnet, the direction is from North to South Pole, and inside the magnet, the direction is from South to North. Number of magnetic field lines is nothing but a magnetic flux. It is denoted by letter phi, and it is equal to the pole strength M. The pole strength is measured in unit Weber. Next term is the magnetic flux density. It is also known as magnetic induction. It is simply magnetic flux per unit area, that is pi by A. Its unit is Weber per square meter. It is also known as Tesla. 1 Tesla is equal to 10⁴ Gauss. Next term is magnetic dipole. As we have already discussed, there are two poles, inseparable poles in the magnet. These are known as magnetic dipole. What about magnetic dipole moment? Because of this particular dipole, there will be a force, and that can be expressed in terms of the dipole moment, or it is also known as strength of magnetic dipole. In this case, we are considering the coil of area A, and the current I is flowing through this particular coil. The pole strength which is produced, or magnetic field which is produced over here, is represented by pole strength M. It is equal to current I into A. The pole strength is measured in unit Weber, or you can say it is ampere into square meter. And the torque, or you can say the dipole moment, is denoted by letter tau. It is equal to M into B, where B is nothing but magnetic induction. It is pi by A. Next is the intensity of magnetic field, or magnetic field strength. intensity of magnetic field is defined as it is force experienced by a unit north pole in the magnetic field, and it is H is equal to F upon M. M is nothing but a phi, so F upon phi, so its unit is Newton per Weber, or it is ampere turn per meter. Sixth quantity is magnetization. The magnetization is defined as magnetic moment per unit volume and denoted by letter M. This is magnetic moment per unit volume, or this M is proportional to H. Magnetization increases with increasing in the intensity of magnetic field H. So M proportional to H, or M is equal to Xi into H, where Xi is known as magnetic susceptibility. The next term is magnetic susceptibility. It is nothing but a magnetization produced in the material divided by magnetic field applied. In simple words, it is Xi is equal to M upon H. The magnetization is easy if Xi is very high. Relation between B and H. B means magnetic flux density and H means magnetic intensity of magnetic field. As we are knowing that magnetic material, when it is kept in the magnetic field, magnetic induction is because of two things. Number one, it is because of external applied magnetic field H. It is also known as magnetizing field. And number two, it is the magnetization of material itself. And that is why it is given as B is equal to mu 0 into H plus M, where mu 0 is nothing but a permeability of the free space or say vacuum, and it is equal to 4 pi into 10 to the minus 7 Henry per meter. Again, just simplifying this particular equation, you can get this particular value, mu 0 into 1 plus Xi. 1 plus Xi is nothing but mu r. It is known as the relative permeability, and this mu 0 into mu r is known as mu. It is nothing but absolute permeability of the medium. Number 9, absolute permeability. It is a measure of degree to which this field can penetrate through the material. B proportional to H, or B is equal to mu H, or mu is equal to B upon H. So mu is nothing but a ratio of magnetic induction to magnetizing field. Its unit is Henry per meter. Relative permeability. It is nothing but a mu upon mu 0. It has no unit. What is the relationship between mu r and Xi? Relative permeability and the susceptibility. We are knowing this particular equation. Just solve this equation, we are getting this particular value. Again, B is also equal to mu H according to this equation. So just equate these two together, so you are getting ultimately mu r is equal to 1 plus Xi. And the last term, it is about Bohr magnetron. It is the smallest magnetic field or magnetization possible. Below this value, no one can find the value of the magnetic field, that is mu b will be equal to EH upon 4 pi m, where E is charge on electron, H is Planck's constant, and M is the mass of electron. After substituting these values, we are getting 9.28 into 10 to the minus 24 amperes square meter. This is the smallest value which is possible for any magnetic field. So these are the basic terms which are required to understand magnetization. Now we'll turn over to the actual curriculum which is prescribed by SPPU Pune for first year engineering under the course physics. Origin of the magnetization. There are three sources. Number 1, electron orbital motion. Number 2, electron spin motion. And number 3, nuclear spin motion. The logic behind magnetization is that when any charged body is revolving or moving through the material, it produces the magnetic field. Whenever we are talking about the electron has two motions, the orbital motion and the spin motion. Because of the orbital motion, it has this particular value. The magnetization or magnetic field is this much. Because of the spin, it has plus and minus spin, that is plus half and minus half. So it is along with this orbital motion, it is also going to have the spin. So because of these two, it has the magnetization. At the same time, nucleus is also spinning, where protons are present and protons are positively charged particles. But you will find that as protons are having more mass, it is 1836 times greater than that of the electron, this particular value is very, very small and it is neglected. So basically you have to understand that the magnetization is because of orbital motion and the spin motion of the electron. Again, you have to remember that the spin motion of the electron is contributing more, and that is why spin plays a very important role in deciding the magnetic characteristics of the material. When material is placed in the magnetic field, the atomic dipoles, that is atomic magnets, are responding to the external magnetic field. The way in which they are responding, depending upon that, there are these types of magnetic materials. Diamagnetic material, where atomic moments are weakly aligned along opposite direction of the external magnetic field. When material is placed in the magnetic field, and if atomic moments are aligned exactly opposite to the external field and these are weak, then it is known as diamagnetic material. In case of paramagnetic material, they are weakly aligned in the same direction, whereas in case of ferromagnetic material, they are strongly aligned in the same direction. So this is how you can have these three types of materials. Along with these three types of materials, there are two more materials. So diamagnetic, paramagnetic, ferromagnetic, antiferromagnetic and ferrimagnetic. These are the types of magnetic materials on the basis of relative permeability. Again, in short, what is the crux of that discussion? If you are talking about diamagnetic material, it can be pictorially shown like this. This is external magnetic field and the magnetization is deviating. Magnetic lines of force are deviating from that, and this is the picture which is shown when external magnetic field is absent, and this is the picture which is shown when external magnetic field is applied. External magnetic field is from left to right and the alignment of atomic magnet is from right to left, exactly in opposite direction, but the strength of that particular magnetic alignment is very less. So this is how you can consider it. This is the material as a diamagnetic material, where the magnetic lines of forces are deviating away. In this case, if you are talking about relative permeability is less than 1 and the susceptibility is negative, that is less than 0. Diamagnetic materials are the bismuth, silver, copper, hydrogen, etc. Turn over to the next material, that is paramagnetic material, where there is no deviation of the external field. External field can permeate or penetrate through the material also. So this was the situation prior to application of the external magnetic field, and this is after applied in the magnetic field. If you observe, the magnetic field which is applied is from left to right, and the alignment of atomic magnets is also in the same direction, but it is weakly magnetized. So such a type of materials are known as paramagnetic material, where value of relative permeability is greater than 1, just greater than 1, and the susceptibility is positive, but it is less than 1. For example, aluminium, tin, magnesium, etc. are showing the paramagnetism. The third material, which is very important, it is ferromagnetic materials, which has wide applications in the technology. In this case, large number of magnetic lines of forces are penetrating through the material. They allow the magnetic lines of force to penetrate through, and you can observe they are already aligned. Atomic dipoles are already aligned over here, but after application of external field, they are exactly aligning in the same direction, and the magnetization which is produced is very strong. So this is known as the ferromagnetic material, where this value of mu r is very high as compared to 1, and susceptibility is also more than the 1. Again, one thing which is to be remembered over here is that when such a type of material is heated after certain temperature called Curie temperature, ferromagnetic materials behaves as a paramagnetic material. So it is the minimum value of temperature at which ferromagnetic material converts into paramagnetic material, and the value is given as susceptibility is equal to C upon T minus Tc, where C is constant, T is nothing but a temperature, and Tc is nothing but a Curie temperature. So above Curie temperature, ferromagnetic material converts into paramagnetic material. The best examples of these ferromagnetic materials are iron, nickel, cobalt, etc. The fourth type of material is anti-ferromagnetic material. Just observe this picture, where it is observed that the spins are parallel but in opposite direction. So this is known as anti-parallel spin with equal magnitude. Whereas in case of ferrimagnetic, the spins are anti-parallel but having unequal magnitude. So if spins are anti-parallel but equal magnitude, the material is known as anti-ferromagnetic material, and if the spins are anti-parallel but unequal in magnitude, then it is known as ferrimagnetic materials. So in presence of the strong magnetic field, these are weakly magnetized in the direction of field. Magnetic moments are anti-parallel and equal. So these are the materials: manganese oxide, ferrous oxide, cobalt oxide, nickel oxide, chromium, manganese, etc. are showing this type of characteristic. Antiferromagnetic below nil temperature and above which it is paramagnetic. Material is antiferromagnetic below temperature Tn and above it is paramagnetic. Similarly, we can talk about this particular material. The main thing which is to be remembered is that in antiferromagnetic material, spins are equal but opposite in direction. Ferrimagnetic material, spins are unequal and opposite in direction. Another way of classifying the magnetic materials is the soft magnetic and the hard magnetic material. In case of soft magnetic material, magnetization is very easy. In hard magnetic material, magnetization is rather difficult. Again, retentivity of the magnetization is not there in case of soft material, and in case of hard material, the retentivity is more. You can have the permanent magnets with the help of this hard magnetic materials. In case of soft magnetic materials, susceptibility and permeability are very high. In case of hard magnetic material, both these are low. Soft magnetic materials are widely used in AC applications like electric trains, etc. and in case of this hard magnetic material, these are used to produce electroacoustic transducers like speakers and microphones, because there we want the permanent magnetization. In short, this can be the difference among these three materials, which can be shown just by a picture. Here, magnetized in opposite direction, weakly magnetized in the same direction, strongly magnetized in the same direction. The magnetic lines of forces are deviating. Here they are penetrating but in less proportion. In this case, penetration is very high. This is the chart which is giving the comparison among diamagnetic material, paramagnetic material and ferromagnetic material. You can go through this particular chart. It's simple, and that's why I'm not going to explain this particular chart once again. What are the applications of the magnetic materials? Applications of the magnetic materials are wide in the technology. We are going to study three applications. One of the applications is a core of transformer is made up of magnetic material. The mutual induction is quite possible with high performance if we are using core as a magnetic material, so that the magnetic lines of force which are produced by the primary can be cut by the secondary, so that the induction can happen from the primary to the secondary. And for that purpose, we are using amorphous steel, ferrite materials, carbonyl iron core, silicon steel. Laminated magnetic core is widely used to reduce the eddy current losses. Eddy currents are nothing but the circulatory currents which are generated there in the material, and they are producing the heat, so that there will be a loss of magnetization. To avoid that, the core will be used in the form of laminations, in the form of sheets. The second application is the magnetic storage device. As we are knowing, the floppy disk, pen drives, magnetic tapes, etc. These are nothing but the devices which are used to store the information of the data, and that information is stored in the form of magnetic field, that is in the form of the polarities, whether it is NS or SN. Suppose NS is storing 0 and SN is storing 1, then such a type of 0, that is binary bits, can be stored by making use of this property, magnetic field. In this case, we are using reading head to read the information, and writing head which is used to write the information. Whenever we want to write the information on this particular disk, at that time we will be using this particular head. The current will be allowed to pass through this in the form of the signal, and that will be written as a polarity, either SN or say NS, so that there will be a 0 or say 1 will be recorded on that. Similarly, while the data is being read with the help of reading head, whatever the induction which is going to produce over here will be catched by this reading head, and the signal will be given to the processor, so that we can understand what is written on this particular disk. So this is how the magnetic storage device is. So reading and writing, that is a retrieving with good efficiency, is the motto of this particular storage device. But there are chances of losing the data when the temperature goes above the Curie temperature. Another application is a magnetic material as a magneto-optical recording. Magneto-optical stands for, here we are going to use two energies. One is the magnetic energy, another is optical, means light energy. So we can use the light, polarized, monochromatic, coherent light, to write and read the data. And one thing which is very important in this case is that this particular data can be erased from that particular disk. If the disk is rewritable. So by making use of this laser light, we can use this particular magneto-optical recording process. So again, we can have this particular writing of the data by using laser beam. It modifies the magnetic polarities so that the writing is made possible. So whenever you want to write 0 or say 1, you can have the polarities NS or SN. Reading the data. Data can be also read by making use of this laser light. So the polarization of this magnetic atomic magnets can be understood just by using this laser light. Again, erasing the data. Data can be erased just by applying magnetic field in the reverse direction. Or laser can be focused on that so that the surface can be heated above Curie temperature so that data can be erased. So this is how the magnetic materials are. So one thing which is very important and to be remembered is that you have to remember the basic terms. Again, what is the origin of the magnetic field? Origin is because of the orbital motion and the spin motion of the electron. Similarly, nucleus is also contributing, but the most powerful contribution is from the spin of the electron. After that, we have studied the types of materials, that is ferromagnetic, paramagnetic, diamagnetic, antiferromagnetic, ferrimagnetic, and another way it is nothing but a hard magnetic material, soft magnetic material. And there are three applications for as a transformer core: magnetic storage and magneto-optical storage.